And if we aim everything just right, we get a conveyor belt of energy. We steal it from the Earth, give it to Jupiter, and then come right back. And in fact, we can use hundreds or even thousands of asteroids this way, continuously stealing Earth's energy and dumping it toward Jupiter. And before you know it, the Earth is falling into a fiery plummet.
First, you need to catch an asteroid. It's as big as a mountain, and it's traveling around 10 miles a second. Next, you need to attach rockets and boost the asteroid onto the perfect course. Next, repeat, thousands and thousands of times. Very slowly, over thousands of years, the Earth will fall towards the Sun. Right now, we're just over 90 million miles away. By 70 million, the Earth is a superheated desert like Venus. Then things start to get really bad.
As the Earth slowly spirals into the Sun, a series of events unfolds which unfortunately spells doom for our planet. As the Earth approaches the Sun, the atmosphere heats up and blows off, and the oceans boil, basically turning the Earth into a giant comet. But there's worse to come. As the Earth gets closer to the Sun's gravity pulls on the near side of the Earth more than it pulls on the far side, and the Earth stretches like putty. At some point, it gets close enough to the Sun that the Sun's gravity can overwhelm the Earth's gravity, and it shatters, pulverizes our planet.
The Earth is dead, but its ghost could remain, a faint ring of material around the Sun. Peter Schultz, planetary impact geologist.
If the Earth or any object gets too close to another object like the Sun, eventually the tides will rip it apart. As that happens, it would simply be broken into many small pieces that would then encircle the Sun as if it were a ring.
The Sun would resemble Saturn with its own faint ring of rocks and dust. A fiery death and a ghostly remnant. If you want to destroy a planet, this could be the way to go. Maneuvering billion-ton chunks of rock with pinpoint precision at hundreds of miles a minute is quite a stretch. Not to mention the amount of time it would take to capture enough asteroids. We've tried to crush it and burn it. It's time for another plan. An antimatter bomb. Physicists have been searching for over a century for a theory that unites our understanding of the large-scale universe, planets, galaxies, and stars, with what we know of the subatomic world, electrons, protons, and quarks. Their theories are bringing to light some pretty destructive phenomena. One of them could be a world killer. Antimatter. Theorized in the 1920s, detected in the 30s. Now we can create antimatter in modern particle colliders. And the base ingredient for the biggest explosion possible. Antimatter is the most explosive substance ever found. Pound for pound, it's far more powerful than even a hydrogen bomb. But antimatter is hard stuff to find. Everything we see around us, out to the most distant galaxies, is matter, created 13 billion years ago in the Big Bang. It created antimatter too. They look similar. In fact, they are entirely opposite. Put them together, and they wipe each other out. Cosmologist Lawrence Krauss.
For every particle in nature, there should be an antiparticle of equal mass and opposite electric charge. And when you bring those particles together, they can annihilate into pure radiation. There's no way that you can get more energy out of a particle than annihilating it with its antiparticle, because all of the energy from its mass goes into radiation. Now I have a proton here, and anti-Krauss over there has an antiproton. And when we bring them together, we're going to make an incredible explosion. Okay, let's annihilate.
This is what happened to all the antimatter created in the Big Bang. It annihilated. If we want to use some for a bomb, we need to make it ourselves. Making antimatter is a bit like firing a gun at a target.
If I shoot a gun at a paper target, the paper that flies out of the target is like matter, and the hole that's left behind is the antimatter. It takes energy to create a matter-antimatter particle pair. In the shooting range analogy, the bullet provided the energy.
In reality, the gun is a particle accelerator, like the one at CERN in Switzerland. The world's largest high-energy particle accelerator doesn't just potentially create black holes as a byproduct of its work. It also creates antimatter because of the high-speed collisions that occur.
And if those particles are moving with a speed so that their energy is high enough when they bang on a particle of matter, there's enough energy to create a whole new particle of antimatter. They do that. And so they create, very sparingly, antiparticles.
It's vast. The whole facility is underground. Even the particle detectors are as big as houses. All this to learn about particles last seen in the universe just after the Big Bang. The incredible energy of that explosion created many exotic forms of subatomic matter. And alongside it, the Big Bang also created antimatter. The universe we see today is made up of the matter left over once all the antimatter was gone. Which is why we have to make it from scratch in particle accelerators. Fire protons in a giant tube, steer them around with powerful magnets, use the same magnets to accelerate the protons to near the speed of light, then slam the beam into a block of metal. For every million protons that hit, you get one antiproton. It's as if Plate's handgun only left a hole once in every million shots.
In an accelerator, you only get one particle-antiparticle pair out of every million collisions or so. And so it's really hard to find that one antimatter particle floating around. It's a lot like coming to Niagara Falls and trying to get that one particle out of all the mist. And that's why it's so hard to create antimatter on a large scale.
Assuming we can obtain enough antimatter, the next challenge is to make it into a bomb. But nothing is more unstable than an antimatter bomb. You have to find a way to hold the antimatter without it touching any ordinary matter. If it does, it will explode.
So I have a bunch of antimatter above my hand here. Well, it better not touch my hand, because if it does, poof, okay, at a huge annihilation. But worse, it can't interact with the air around it, because the air is made of matter. And again, you'd get an incredible explosion.
Researchers need a special container to study antimatter. And this is it, a penning trap. Powerful magnets suspend the antimatter in a vacuum.
So if I want to store this antimatter, what I have to do is somehow keep it levitated above my hand, which means I'd have to produce huge magnetic fields in just the right way to keep the charged particles in the antimatter from touching my hand. But I'd also have to store it in an incredibly high vacuum, because any air in the container would again cause an explosion. And so the energies and technology required to produce those magnetic fields, keep that ultra high vacuum, would mean that you wouldn't have a small object. You'd have to have surrounded with massive amounts of machinery.
So far, mankind has managed to create a grand total of 20 nanograms of antimatter. That's 100 million times lighter than a dime in your pocket. So the bomb is going to be too small even to see.
Well, 200 feet away in this test range in Arizona, we have the explosive equivalent of TNT. So let's see how big of a bang that makes. Wow.
20 nanograms of antimatter makes quite a blast, but it's way short. To destroy planet Earth, we would need 2.5 trillion tons of the stuff. That's a bomb the size of Mount Everest. At the bottom of a hole 4,000 miles deep. If it were possible, the result would split the Earth into thousands of pieces. With a powerful enough bomb, the pieces would fly out into space and are lost. With a slightly weaker bomb, the pieces fall back under the force of their own gravity, collapsing into a molten ball. An eerie echo of Earth's creation 4.5 billion years ago. It could happen, in theory, but there are a few technical details to iron out first.
So what's the matter with antimatter? Well, if you're trying to destroy the Earth, it'll work. It'll do the job. The problem is you need about the energy that the sun puts out in an entire week. So it's a huge amount, and we just don't have the technology to create that right now.
At the present rate of production, making the bomb would take more than the age of the universe. So, as a way of destroying the Earth, maybe antimatter has some problems. But we know the next approach works, because it already happened once before in Earth's ancient past. Space is a dangerous place. It's full of debris. Rocks the size of pebbles up to rocks near the size of a planet. There are impact craters everywhere, including our moon. These asteroids can hit us as well. An asteroid wiped out the dinosaurs. Maybe a bigger asteroid could destroy the planet entirely. Meteor Crater, Arizona. Almost a mile across, nearly 600 feet deep. Today, science can reconstruct what happened here thousands of years ago. Dr. Dan Durda, planetary scientist.
You wouldn't want to be standing here 50,000 years ago. This iron meteorite, about the size of a small office building or so, it's made out of stainless steel from space. It's about to strike the desert with an impact energy of somewhere between 1 and 10 megatons. And it's that energy that's going to excavate and open up this crater behind me, which is nearly a mile across.
The impact ultimately devastated an area the size of New York City, with 600 times the power of the Hiroshima bomb. And that was small. 65 million years ago, a real monster struck. It was 6 miles across. Sat on the ground, it would outtop Everest by half a mile. The crater was over 100 miles wide. The impact wiped out the dinosaurs and destroyed most of life on Earth. An even bigger space rock could destroy the planet. We're already developing technologies to protect against future impacts. Ironically, you could use those same technologies to make an impact happen. One approach is to hover a space probe near the asteroid. The probe's mass generates a tiny gravitational pull on the rock.
Many of the other techniques for moving asteroids require us to know something about the asteroid itself, what it's made out of, how its surface might respond to being pushed or pulled on, what the shape of the asteroid is or how fast it's rotating. The gravity tractor requires us to know none of those things. What we do is we park the spacecraft near the asteroid. Under ordinary circumstances, the self-gravity between the spacecraft and the asteroid will cause each other to slowly attract and settle together. In the case of the gravity tractor, however, we use the ion thrusters on the spacecraft, and these are common thrusters. We fly them in space already, so there's not much new technology needed. Rather than having the thrusters impinge on the asteroid, we cant them off to the side so they don't actually push on the asteroid. Under normal circumstances, that would cause the spacecraft to tend to accelerate away, but in this case, the self-gravity between the spacecraft and the asteroid keeps the two glued together, and as the spacecraft slowly accelerates away, is now going to tug and pull the asteroid along with it, using gravity as the tow line.
Over time, that can change the asteroid's course enough to miss the Earth, or to guarantee a hit. Another protection technology that we could use is a technique called solar sublimation. This diverts an asteroid or comet using nothing more than sunlight. To demonstrate the effect, Durda starts by building a homemade comet.